Welcome to our course NPTEL courses on the advanced power electronics and control. We shall continue with your rest of the PWM techniques. We will start with the sine PWM, thereafter we will try to cover multi-level inverter. So, as we were discussing in my previous class that sinusoidal PWM actually an extension of the multipulse PWM, where actually the modulating waveform instead of the square wave will have a sine wave. In this method several pulses per half cycles are used as in case of the multiple modulations, but each pulses is modulated proportional to the amplitude of the sine wave. So, in case of the multipulse converter in a square wave, you got all the pulses have the same width, but you will have a variable frequency, a variable width pulses throughout it. In central of the fringe you will have actually more width, in the zero crossing you will have a less width. Gate pulses are generated by comparing the sinusoidal reference signal with triangular carrier signal. Frequency of reference signal FR decides the frequency of the output voltage. The ratio of VR by Vc is called the modulation index, which controls the output voltage, and number of pulses per half cycle depends on the carrier frequency, the ratio of this actually the carrier frequency and the modulating frequency. There is a two type of the SPWM. One is bipolar, another is unipolar. Bipolar will have a more harmonic and more disadvantages for actually time constraint. We are going to discuss only the unipolar switching technique. The bipolar output voltage waveform contains more harmonic than the unipolar PWM. So, for this reason our discussions will be considered only the unipolar PWM. So, this is a triangular wave and it has a frequency as much as high as actually 20 times, and you have a sinusoidal waveform. You can see that at the zero crossing width is less and will vary like this. And if you have this kind of pattern, so this is called the unipolar modulation. It is very easy to implement. So, in one half cycle you have a shifted wave, thereafter when it is a negative half cycle multiply with that -1 and you will have this shifted wave, and accordingly the carrier will be gate pulses will be generated, and this will be compared with the op amp, very simple circuit, modulating signal and carrier signal. Bandwidth of the op amp required to be at least 10 to 15 times higher than the carrier wave to operate it properly, and then you will have a pulses. So, modulation index. Modulation index is the ratio of the peak magnitude of the modulating waveform and the carrier waveform. So, M equal to Vm by Vc. So, this Mi modulating controls the harmonic content of the output voltage. We will see it how does it done. By increasing the number of pulses n per half cycle, the lower order harmonic get cancelled, and what happen actually you are shifting the spectrum to the ratio types. If it is actually 1 kilohertz carrier frequency and 50 hertz cycle, so you will be shifting this actually this frequency band multiple by the 20 times more. So, but higher order harmonics will get increased, that is the basically the issue. Higher order harmonic can be filtered out easily, because essentially your all those devices, you got a copper, it has got inductor, all the machines will have a inductors, your conducting line will have an inductor, and thus all will actually help you to actually minimize the effect of the higher order harmonics. Higher value of the n is more, but leads to more switching lots, and that will reduce the efficiency of the inverter. And moreover, we have discussed about the devices, if we have a prescribed frequency for the prescribed switching frequency for the prescribed devices. If it is GTO, it cannot be operated over and above around 2 kilohertz. So, around if you wish to go above the 2 kilohertz, you have to be settled with the IGBT. So, power rating is quite lower then, and then if you take higher than this IGBT, you have to switch over to the MOSFET. Then MOSFET can handle power only in the range of the hundreds of watts. So, this is the basically that we have to see to it that it is not a constraint that we can increase the carrier frequency. Nowadays, we have a very high processor and it can generate the digital pulses at a very high switching frequency, but constraint also imposed by the switches. So, what is over modulation? When peak magnitude of the modulating signal exceeds the peak magnitude of the carrier signal, the PWM inverter operates under over modulation. During over modulation, the output voltage increases slightly, but you will generate more and more harmonics. So, harmonics, there is a IEEE standard, IEEE 519, all those standards are there, that it actually tells that the value of the harmonics of 5% allowable in an inverter output voltage. So, voltage THD required to be around 5%, but inverter output voltage contains more than 5% harmonics. Filter can be used to reduce the harmonic content. So, that is the actually the bottom line of it. You have to, when you are giving to the customer, so THD content has to be less than 5%. Smaller the size of the filter is enough for reducing the higher harmonics, and thus it is become a natural choice to use sine PWM with higher switching frequency. But bigger the size of the filter, it is required for reducing the lower order harmonics. It makes the system costlier and leads to the poor performance of these devices, and hence the system without filter is need to be suppress the harmonics. Now, you see that let us now do the analysis of the unipolar PWM. So, you have triggered an angle alpha, again it will be triggered after angle alpha 2 and so on, and we will have a this kind of variable frequencies. So, we can find it out, we have a odd wave symmetry, thus only sine component will be preserved, and so Bn will be 4 by pi Vs 0 to alpha sine n omega t d omega t, thereafter minus, because here you get minus alpha 1 to alpha 2 sine n omega t d omega t, plus again actually alpha to pi by 2 till this much sine n omega t d omega t. So, if you can substitute and you can get Bn equal to Vs by pi 4 Vs by pi 1 minus 2 cos n alpha plus 2 cos n alpha 2 by n. Now, you can actually, this is the concept of selective harmonic elimination technique. You can choose the, you can make the value of the Bn is 0 by this term equal to 0. So, you can, so if you have a 2 pulses for this system, actually you can choose the alpha 1 alpha 2 and solve online to make this value 0, and that particular harmonic can be eliminated. For example, you take a case that we want to eliminate the third harmonic and the fifth harmonic, and rest of the harmonics is higher order. So, it can be filtered out. So, the equation is actually for Bn, you can substitute, actually all those things will be 3. So, you will get these equations, and for fifth harmonic you will have this should be equal to 0, and ultimately you boils down to this equation, and you can solve, and while solve your alpha 1 should be 20 3 degree and alpha 2 should be 33.3. So, what is the advantage of it? So, you can eliminate alpha 1 and alpha 2 alpha by and thus get rid of the lower order harmonics like third and fifth. And by using the same equation, we should have a multiple pulses. We can eliminate the 7th harmonic, 9th harmonic and the 11th harmonic, and so you can find it out that if actually third and fifth is eliminated, so what should be the harmonic content of the 7th harmonic, what should be the harmonic content of the 9th harmonic, what should be the harmonic content of the 11th harmonic. So, accordingly whether you are getting THD as prescribed by the standard or not. Now, the amplitude of the fundamental component of the value alpha 1 and alpha 2 is, so you can substitute these values. So, ultimately the fundamental value will have a 6% increment. So, that is 1.06. The amplitude of the fundamental component of the unmodulated waveform is actually 4 Vs by pi. So, that value is essentially 1.27, but it will have a degradation of this value from this unmodulated waveform, but you get lower THD. The amplitude of the fundamental waveform is 83% of the unmodulated waveform. So, inverter is derated by 16% if you wish to use this Sinusoidal PWM with selective harmonic elimination. The additional 8 computation per cycle is increases also due to the switching losses. So, these are the few take on from the multi pulse sine wave inverter. So, now let us discuss about a very important topic, that is till now we are discussing about your PWM inverter. Now, we shall discuss inverter topologies, that is multi-level inverter. Why we require a multi-level inverter? Essentially what we have discussed till now, we have restricted ourselves to the 2-level inverter. Why you require multi-level inverter is that first of all there is a logic behind it. Let us consider a simple buck logic, but it has to be, since it is an AC, so it has to be like this. But what essentially you are doing, you can while you are switching on, you can have this voltage or 0. Ultimately you will have that volt area match with this, or you may have a sinusoidal waveform, or you will actually, so this volt area will match. Ultimately to match this volt area, essentially what you will do, you will inject more and more harmonics. So, but let us consider a simple case of when you switch on, it gives 12 volt, but you require a 5 volt instantaneously. So, you will match, you will apply 12 volt for small interval of time, rest of the time you will apply 0, and thus you say that actually this volt area matches. Okay, theoretically it is okay, but what happens, the power quality decreases. So, you require a sinusoidal voltage, and once you switch on, when you have almost a 0 voltage, you are applying a whole DC voltage. Then what happens? You say that actually volt area matches, but within that area essentially it is filled up by the unnecessary harmonics. But assume that you have a steps, you can apply 6 volt as well as the 12 volt. So, once we want to generate 5 volt, you can turn on only 6 volt. So, there is a less instantaneous error between the applied voltage and the actual voltage required, and thus the actually unnecessary harmonic generation will be lower, and this is the basic essence of go for the multi-level inverter. So, conventional means actually we say that it is 2 level, and If it is more than 2 level, it is multi-level. It can be any level. So, as I discussed, THD of this voltage waveform at the output of this 2 level inverter will be higher because of instantaneous difference of the applied voltage and the actual voltage, and THD is low with the output voltage because your applied voltage and the actual voltage has less instantaneous error. Since you are switching on whole DC bus volt switch, you are getting plus this, actually the pole of this actually inverter goes to plus minus VDC. So, stress across the switch is quite high, but you have a choice. You may apply VDC by 2, VDC by 4, VDC by 6 depending on the level you have chosen. Thus, you will have a less stress on the switch. Since device is not available to sustain high voltage, and thus this 2 level inverter cannot be used for high voltage applications as well as the high power applications. But it can be used since it can block higher voltages and individual switching rating get reduced in the multi-level inverter. It can be used for the higher voltage rating and applications. And high voltage level cannot be produced like we require maybe the HVDC link and all those things. There is a rectifications and somewhere there is an inversion operation, there you cannot achieve this. High voltage level can be produced by the multi-level inverter. Since voltage drops heavily or builds up heavily while turn off, voltage drops heavily while turn on across the switch and builds up heavily across the turn on of the switch. So, it will subjected to high DBDT and all the switches has to be protected from the ill effect of the high DBDT. And one of the menace of this actually high DBDT is the EMI. So, it will have more electromagnetic radiations and interferences. Since DBDT is less, so EMI also will be less. Since actually we require the same output, same THD because we want to shift the THD. So, if you use the 2 level inverter, we require to increase the switching frequency to achieve the same THD at the size of the filter. And once you increase the switching frequency, you increase also the switching losses. So, it will have the more switching losses. Since it gives a closer THD because of the less error in the instantaneous voltage and the actual voltage. So, size of the filter is already reduced, you need not have to actually use high switching frequency, and thus you can use the higher rating switches and it enhances the power handling capability, and apart from that it gives you the desired power quality. So, due to these all advantages, now we have entered into the domain of the multi-level inverter and we are now living in the multi-level inverter. All the inverter you see that actually if you have a solar inverter, small solar inverter in your rooftop or any other places, that also a multi-level inverter to reduce the size of this actually the filters and apart from the high power applications. Now, let us see the classifications of this inverters. Multi-level inverter can be broadly classified into the 3 categories. Sometimes it is actually this can be this coupled and this has been kept aside. So, anyway we decided to actually go by conventional classification. One is actually diode clamp multi-level inverter. We see the topology, we will find that actually there are many diode put into the system, and if the level goes very high, the number of diode is also increasing like anything anyway, so we shall see that advantage and disadvantage of the diode cam multi-level inverter, followed by flying capacitor multi-level inverter. So, we will find that actually voltage, multiple stage of the voltage is generated by the multi-level inverter. Thereafter cascade bridge multi-level inverter. These are the three multi-level inverter. These two can use a common DC source. So, one DC source can be used for all the applications, and thus we have a operating advantages, but component count will be more, and generating higher level, it is basically very complex and it becomes bulky. And whereas in a cascade multi-level inverter require all those multi-level entities require separate DC source, but it has a very big advantage that it is modular in nature. You can level them up to any level by the separate DC voltage. So, these are the three main entities of the multi-level inverters. Now, let us go to the diode cam multi-level inverter. So, here we can generate, this is basically a 5-level multi-level inverter, and there is some calculations has been written. So, please understand that. Choosing devices at 2m minus 2. So, these are the IGBTs are here are the switching devices. So, it is a 5 level. So, it tells that basically you have 2m minus 2, 1, 2, 3, 4, 5, 6, 7, 8. So, you got 8 such devices, and if it is a 3 level, so you make it actually 3 here. So, you will get 4 devices. So, this much to this much will give you the 3 level. A number of voltage source in this case is basically what you require is a capacitor. It is basically this, there 4. So, that should be m minus 1, but problem lies with the number of diodes, and it is increasing obnoxiously. It is increasing like anything, like rumor. So, that value is basically m minus 1 into m minus 2. So, here it is 4 into 3, that is 12 diodes. So, think about if you have 11 level inverter, so how many diodes would be there? So, that is one of the drawback of this topology. It employs huge amount of the diode. Every diode basically consisting of the losses of 0.7 volt, and it is a, since it is a power diode, it generally have a losses of around 1 to 2 volt. And what happen, while having a path, you will find that it always flows through, every single phase flows through at least one diode at a time, one switch and one diode. We will discuss this conduction of different type little later, and then what will happen, that this will leads to a huge loss of efficiency. And voltage across each capacitor, you can, it is the same thing, that is VDC by m minus 1, and this is something while we will studying the output you will get, that is the line voltages. Here you will have steps of line voltages, that is actually 9 steps voltage will come, that is basically 2m minus 1. So, you see that how it operates. So, if you wish to get that voltage at the point A, that is the pole of the inverter, required to get VDC all the upper switches, all the 4 upper switches required to be on. So, SA1, SA1, SA2, SA3, SA4, and this has a this has basically a simple logic. I do not have time to discuss because this switch and this switch is complementary. Similarly, this switch and this switch is complementary, this switch and this switch is complementary, and this switch and this, and we can see that here from this table also. So, all the upper switches is on, then you get the voltage equal to VDC, that is 111. So, here you get the voltage of VDC, and the lower should, and all the lower switch should be off. Once you get, once is to get basically 3 VDC by 4. So, this voltage, this switch required to be off, this voltage required to be off, ultimately this will be the direct forward biased, and this till this to this it will be all on. So, all the 4 you will see that at a time all a set of 4 switches are on, and gradually it will shift one by one. It is just like a shift resistor, very easy to design this kind of circuit in a digital domain. So, these all will be on, and since they are complementary, there will be 0. So, you will get the voltage of plus 3 VDC by 4, and similarly, if you wish to get VDC by 2, so here these two switch should be off, then actually D7 will take care, and these 4 switches will be on and lower 2 switches will be off. Similarly, for D4 you will get all, and if you wish to get 0 voltage, then all the switches should be on, lower switches should be on, and ultimately this point should be connected to the this point, and it is assumed to be the 0 voltage. Now, what are the advantage and the disadvantage of direct clamp multi-level inverter? The large number of levels can be yield, and thus we will have a lower THZ, and it is a general advantage of all the MLI, not only this MLI. All the phases shares a common DC bus, thus you do not require a multiple voltages and multiple sources. We will see later reactive power flow can be controlled. In this configuration, we can have a DQ control, a different kind of control technique is employed. Mostly these are uses for the wind farm applications, all those cases, or the high voltage application where we require to have a PQ control. High efficiency for fundamental switching frequency, that is something we require to understand it. Fundamental switching frequency, we have seen that in case of the selective harmonic elimination, it is reduced by around 18%. But here we shall see that it has got a higher switching, higher efficiency, and relatively simple controls that comes with the comparison with the other 2 MLIs. These are direct clamp and actually cascade multi-level inverter, because instead of a direct clamp, capacitor clamp multi-level inverter has a huge number of capacitor, and each voltage is actively maintained, and thus require more complex control. Similarly, for the cascade multi-level inverter, we require to have a multiple voltage source, and we all assume that voltage required to be constant. So, these are few challenges These are few advantages of the multi-level direct clamp multi-level inverter, but of course, there are so many disadvantages. So, we shall discuss the disadvantages and we will switch over to the next multi-level inverter. Thank you for your attention. We are looking forward to a very exciting next class also.